Hello, welcome to all. In the previous lecture, we started the new unit, Electromagnetic Induction. Okay, as a part of that, we discussed the phenomena of electromagnetic induction and Faraday's law and integral and differential forms of Faraday's law. Okay, the plan of today's lecture is, you can see the outline here. Today we are going to discuss about the Lenz law, okay, which will give you the direction of the induced EMF. Okay, after that we are going to discuss about self-induction and inductance and EMF of self-induction, and finally we are going to discuss about the inductance or self-inductance of the solenoid. Okay, in which case we already know the magnetic field. Okay, by using that, in today's class we will derive the expression for the self-inductance of the solenoid. Okay, what is Lenz law? You can see this on the slide. The direction of the induced current is such that it opposes the cause that is generating it, the cause that is generating it. That means, what is the cause here? The change in the external magnetic field. Okay, so the current is induced in a coil placed in the varying magnetic field such that it opposes the change in the external magnetic field, which is in turn the cause of the induced EMF. Okay, so in some other way you can also state this. Okay, the induced current, here the induced current is behaving like this. Say the induced current is, see what happens when you have the current in the conductor. Obviously, from the Oersted's discovery, you have some magnetic flux, okay, around that loop. Okay, this flux, the induced direction of induced current is such that this flux opposes the changes in the flux that is responsible for the induced current. Okay, you may also state Lenz law in this manner. Okay, in the first statement I did not refer to the flux. Okay, I just referring it as a cause of induced EMF. Okay, here according to Lenz law, the flux, okay, due to the induced current is such that it opposes the changes in the flux, opposes the changes in the original flux. Okay, magnetic flux, original magnetic flux that is responsible for the induced current. Okay, now let us try to understand this Lenz law by taking one example. I am taking one loop. Okay, you see this on the slide. Okay, on the right edge, the magnet is falling into the ring. The magnet is moving inside of the ring. Okay, on the right edge of the slide, you can see this north-south pole. Magnet is coming towards the coil. Here, the what will be the, your doubt is what will be the direction of current, induced current. The direction of the current, according to Lenz, the direction of the current should be like this only, not like this. Why? Because whenever you use right hand thumb rule, the magnetic field lines will be like this. Here, okay, coming out. So you have, you can see in the slide as well. We can, okay, here your field lines will be coming out of this ring. Okay. Your field lines are coming like this. That means here you have field lines like this, like this. That means now, due to this current, induced current, this ring behaves as a magnet. See, by seeing this field line pattern, you can easily identify this as a north pole, this as a south pole. Okay, whenever the magnet is coming towards this ring loop, so that its north pole is facing the ring, then automatically the current will be induced in this loop such that see on the top side of this loop there is always a north pole of this electromagnet. So below this loop you have south pole of this electromagnet. Whenever the induced current is flowing such that here on this side you have north pole, then what happens? There is a repulsion between north pole and north pole. That means it cannot move further. That means what is the meaning of that? If it moves further, the change in the flux would have increased very much. But whenever the current is induced in this loop, after that what is happening here? The fall in the flux, that means the rise in the flux is stopped due to the direction of this induced current. Why? Because this tiny magnet is not allowing this magnetic pole to come inside of this ring. Now this ring is behaving like a magnet such that its north pole faces the magnet's north pole. Then what happens? Usually it stops the magnet coming towards it. That means the induced current is stopping the rise in the flux due to the motion of the magnet. Okay? Yeah, this is Lenz law. So by using Lenz law, to oppose the motion of this magnet or to stop the change in the flux linked with this coil, current must have to induce. The current must have to be induced in this direction only. There is no other way. Okay, that's why we put EMF is equal to minus of the change in the flux, dou phi by dou t. Okay. If you go for the other end of the slide, what is happening there? Simply you just change the poles. Okay, here on south pole you just reverse the magnet and take it away. South, north, your magnet is moving above. Your magnet is moving away from the loop. Then what happens? Whenever the magnet moves away, the change in flux is again negative here. The number of field lines which are inside of this loop will gradually decrease. Now, so the induced current, due to this change, whether this change may be plus or minus, the induced current will be introduced. Okay. If this change is minus, decrease in flux is taking place. This induced current now, or otherwise, the current is induced in such a way that the further fall in this flux is stopped. Okay, that means now what happens here? You see, you are here again. We are having the field line pattern like this. Okay. Here, on this side you have north pole, on this side you have south pole. You may ask, sir, why the direction is again same? Because we flipped the magnet. That's why this pattern will not change. So you see here, this is moving away, but there is an attraction between the south pole and this induced north pole. That's why This induced current is stopping the further decrease in the flux. Further decrease. Okay, it stops either decrease or increasing of the flux. Okay, in the earlier case, it stopped the increasing of flux. In this case, it is stopping the decreasing of flux. Why? Because it is attracting magnet. It is not allowing this magnet to move away from this. Okay, so in this case, your induced current direction have to be like this only. Have to be like this only. Okay. In this way, we can understand the Lenz law. Okay. Here, this can be seen if you interchange the movable part and stable part here in this example, that means you are just placing a magnet here. Okay, you are just allowing the ring, okay, a metal ring to fall on this magnet. Okay, now you are not moving the magnet, you are fixing the magnet, but you are allowing the ring to move, loop to move. Then what happens? Usually in the literature, this is called as jumping ring experiment. Jumping ring. Otherwise, it floats in the air. Okay. The same thing can be constructed in a different way. See, you may take a metal cylinder. You may take a metal cylinder and just you allow the magnet to fall inside. Okay. You take a tiny magnet, you allow this magnet to fall through this cylinder. What happens is, here this is your loop, this is a magnet. Here this is your loop, this is your magnet. Okay. In both cases, what happens is, up to certain extent, this magnet falls inside this loop. But after that, what happens is, due to the induced current in this cylinder, its motion is stopped. That's why it floats in the middle of this cylinder. Okay. What happens here? If you are taking a ring and a magnet, you are allowing the ring to fall on the magnet. Your ring is coming towards, due to gravity, it is moving towards the magnet. See, whenever it moves towards the magnets, okay, number of field lines entering into the ring increases. The flux increases. Now what happens? Some current will be induced in this ring such that further change in the flux through the ring is abated. That means stopped. Okay. So what happens after some time is certain balance is maintained between gravitational force and the upward repulsion force. What happens here? On this side, on the lower side of the ring, north pole will be induced. On the top side of this loop, south pole will be induced. Okay? After some time. Then what happens? Then you have repulsion between these two poles. That's why its motion will be retarded or it is stopped due to the balancing between the different forces acting on the ring. That means gravitational force will be downwards of this. Next, magnetic force will be upwards. F gravitational, F magnetic. So after some time, what happens? Equilibrium situation arises. Then this ring simply floats on the magnet. That means here you have magnetic field lines like this due to the induced current. You have magnetic field lines like this. That means here you have the direction of field lines like this. So this will be the direction of field lines in this case. Okay, this flux, induced flux, is compensating for the actual flux prevailing here. Okay, actual flux prevailing here, right? Yeah, this is what about the Lenz law and its applications. Okay. Yeah. Now let us go for the self-induction. See, in the previous lecture we discussed about the electromagnetic induction. Okay, there you have one varying magnetic field. Okay, you have the varying magnetic field. Okay, uh, in that varying magnetic field you are placing a conducting loop. Okay, actually you have no current. Previously you have no current in that conducting loop, where you are just taking the loop and placing that loop in the varying magnetic field. Okay, varying magnetic field, you are just placing that loop here. Okay, due to the change in this flux enclosed by this loop, you are observing some current, induced current inside of this coil. Okay, this is somewhat different from the higher states discovery. Here the magnetic field, changing magnetic field, creating the EMF in the coil. EMF in the coil. Okay, this is what electromagnetic induction. Okay, right. So due to the change in the magnetic flux, you have the induced current or the induced EMF in the electromagnetic induction. And what is this self-induction? Okay, what is the difference between induction and self-induction? Electromagnetic induction or induction? This is self-induction. Okay, here also you have some current, induced current. Okay, you know that the varying you can see parallelly on the slides as well. Okay, you know that varying magnetic field create the EMF in a conducting wire, okay, or the conducting loop. Okay, that means whenever you place a coil in the varying magnetic field, then what happens? Electromagnetic induction takes place. What is the meaning of that electromagnetic induction? This changing magnetic field over the loop, okay, inducing some current, okay, inside of that conducting loop. Okay, here we are only talking about varying magnetic flux or varying magnetic field. Okay, in the previous lecture we discussed the ways to create the varying magnetic field. Okay, you may select one permanent magnet, or you may take a coil in which some current is flowing. Okay, previous in the previous case you are taking the permanent magnet. In the second case you are taking the electromagnet. Okay, in these two cases you may get the varying magnetic field. Okay, electromagnetic induction is not talking about this case A or case B. Okay, it takes place. Induction takes place irrespective of the cause of the changing magnetic field. Changing magnetic field, that you have to note. Whenever there is a changing magnetic field, whatever may be the cause of that changing magnetic field, induction, electromagnetic induction takes place. Okay. Now let us go for the second case of creating varying magnetic field. Okay. So for that, what we are doing, we are going for the cause, one of the causes of varying magnetic fields. Okay. Suppose that you have some conducting loop or the current carrying loop. Now we are bothering about the cause of the varying magnetic field. Suppose that we are choosing a coil in which some current is flowing. Okay, as you observe the flow of current with respect to time, then if you notice the change in the magnitude of current, then we call that the time varying current. This current can produce the time varying magnetic field, which we discussed in the previous class as well. Okay, by changing the magnitude of current over the time, you can get the varying magnetic field that can cause the electromagnetic induction. Okay, now we are not bothering about that coil, second coil. We are bothering about the coil which is able to produce coil with a current which is able to produce the varying magnetic field. What happens in this wire? What happens in this wire? This wire with this much of current is able to produce the magnetic flux. Magnetic flux. Okay. Here, in the, previously we had a coil in the flux created by this coil. Okay. Then what happened there? The changes in this flux are causing some induced current in that coil. Coil under consideration. Coil under consideration. Okay. Now we are seeing the effect in the cause itself here. Okay. In the previous class, we placed some another coil in the flux of this coil. Whenever this flux changes, an induced EMF is produced in that coil. That is different thing. Okay. Why there is an induced EMF in that coil? Why? Because the flux linked with that coil is changing. Okay. Now leave about that coil. You just restrict to this coil itself. The coil which you are using to produce time varying magnetic field. Okay. Whenever the current flows through this coil, whenever the current flows through this coil, so the time varying magnetic field or a changing flux is created in this coil. Okay, the same flux entered into the other coil where it is able to create electromagnetic induction that we discussed already. Now I am talking about only this coil, the coil which we are using to produce the varying magnetic field. See, this flux is already linked with this coil itself. If this flux, change in this flux is able to create an induced EMF in some other coil, my question is the same, whether the same thing does not happens for this coil as well, whether the same thing happens for this coil or not. Why? Because the same flux linked with some other coil is able to induce some current in that coil. But this flux, these variations of flux already within this coil as well. My question is whether these changes can induce any current within this coil itself. Okay. Yeah, that happens. Here, the variation in the flux is able to create some induced EMF in this coil itself. In this coil itself. Whatever that is happening there, that happens here also. That happens here also. But there, you have only one current, that is induced current. Here, already you are having one current flowing through this coil. Okay. Because of the magnetic field created by this current, again you are having some more current, that is induced current in the same coil. Such type of induction is called self-induction. So how can you define the self-induction? You can see on the slide as well. Generation of induced EMF in a coil due to the variation of current in itself is called self-induction, or you may say it otherwise in a different manner. Any generation of induced EMF in a coil due to the current flowing through it is called self-induction. Okay, you can tell, you may define in this way as well. Okay, here the cause and effect are on the single object. It is a coil, single coil, single coil. Okay, cause of this magnetic field, cause of this change in magnetic field is this current. You are already having a current. Again you are getting a different current. Again you are able to get a different current due to the change in this flux created by this current. Already you are having an EMF. Some another EMF you are getting here. You may call that as a back EMF. Okay, that is a back effect of this current. Okay, the effect of flow of this current. Due to the effect of flow of this current, you are getting that current. That is induced current or induced EMF. Okay, this is what the phenomena of self-induction. Phenomena of self-induction. What is self-induction? Some current is flowing through a wire. So as there is the change in the current, there is some changing magnetic flux around that coil. Now your coil is in the changing magnetic flux. Then you have some induced EMF in that coil. Okay, so generating or producing of such an EMF in a coil is known as the self-induction. Self-induction. Okay, you have to note the chain of events. Current, an EMF is there. It is producing magnetic flux. Magnetic flux. Again, this magnetic flux is creating the EMF. This is self-induced EMF. What is this? Self-induction or self-induced EMF. It is simply induced. It is simply, in the earlier case, we have only induced EMF. Now we have self-induced EMF. Self-induced EMF. Okay. This EMF is due to this ordinary EMF. Okay. The current flowing through this wire is able to induce some EMF within this wire. This is known as a self-induction. Okay. Right. Yeah. Here, which constant characterizes this self-induction? We define a constant called L. We call this as inductance as well. So for every loop, every conducting loop, you have some self-inductance. Self-inductance or inductance. Now we are going to define this inductance. This will give you how much self-inductance is there in that coil. Okay. Yeah, what is the exact definition of this inductance? Inductance. Inductance. Okay, it's a new physical quantity we are going to define. This will characterize the self-induction of a coil. Self-induction in that coil. Okay. What is the definition of this? It is nothing but the magnetic flux per unit current in the loop. Magnetic flux per unit current in that loop. See, this is a coil, some current is flowing, I amperes current is flowing. How do you define the self-induction capacity of this coil? How much flux is induced by this current? Otherwise, we reason like this. If you are able to run 1 ampere current through this coil, then how much flux you have? That is what known as the induction of this coil or this loop. What is the induction of this loop? Magnetic flux created by 1 ampere current flowing through this loop. Okay, this is known as the inductance. Okay, it will give you the self-induction capacity of this loop or the coil. Okay, so now actually let us see the origin of this definition, inductance. Okay, now let us study the phenomena of self-induction. You have one coil, you have some current in that, you have some flux, that is induced flux. Due to that flux, you are having one more EMF, that is a self-induced EMF or EMF of self-induction. Okay, because I current is flowing, you have some flux. What is the relation between I and phi? Flux. This flux must be proportional to the current. Why? Because what is the cause of this flux? I. Because you are having some current in this coil, you are having some flux through this coil, some flux through this coil. Okay. Now, if you want to remove this proportionality symbol, you have to introduce one proportionality constant. In this case, we write that proportional constant as L. This is called the coefficient of self-induction or simply induction of the coil, where L is actually it is a proportionality constant. We call this as induction of the coil. Induction of the coil. Induction of the coil. Okay. Now, yeah, you see, we are already studied the definition of inductance. I define this to be, I define this L to be the ratio between phi and I. Why? Because I defined L, inductance, as the flux for the unit current. See, that is actually that definition comes from this relation, this equation, or if you want to define L, this is equal to phi by I. Phi by I. If you make I is equal to 1 amp, if you allow only 1 unit of current to flow through that wire, then you have the induction of the coil as a flux in that case. Flux in that case. So the induction is nothing but the flux, but that flux is created with 1 ampere current inside of the wire. Okay. So this is what the origin of the inductance definition. Inductance definition. Okay. Okay. So what are, I think you know the units of this L inductance. What are the SI units for inductance L? Units. What are the units? Henry. Henry. Inductance. What are the units of inductance? Henry. Okay. By using the same ratio, you may define the Henry as well. Henry. Okay. When it becomes 1 Henry, when it becomes 1 Henry, when it becomes 1, if you make both the numerator and denominator as 1, this is 1 Weber flux current 1 ampere. Then what happens? Then your L becomes 1 Weber by ampere, that is Henry. This is what the definition of Henry. Okay, what is Henry? When we call the induction of the coil as 1 Henry, if 1 ampere of current through the coil is able to create the 1 Weber flux, then we call the induction of the coil as 1 Henry. This is what the definition of Henry. Okay. Yeah, next topic we are going to discuss is EMF of self-induction. In this case also we have some EMF. Some EMF is produced, some EMF is induced. We call that EMF as EMF of the self-induction. EMF of the self-induction. Okay. Now, this EMF is also due to the change in the flux linked with that loop. Okay. So, let us denote this as E as EMF of self-induction. Okay. By using the Faraday's law, you have what is our topic? EMF of self-induction. EMF of self-induction. Okay. From Faraday's law, EMF of self-induction is given by minus of d phi by dt. d phi by dt. Okay. Now this flux is due to the current flowing in that coil itself. Right? Now, if you use the earlier expression which we discussed in the case of self-inductions, which we define to understand the self-induction phenomenon. What is the relation? Actually, from that relation itself, we defined L. Yeah, using our earlier previous relation. What is that? Phi. This phi is given by Li. Okay, I is the current flowing through that loop. Okay. Using this, we have EMF of self-induction is equal to minus d by dt of, in the place of phi, you write Li. Since L is equal to constant, you write di by dt. So what is the expression for the EMF of self-induction? EMF of self-induction is equal to minus of L di by dt. So this is equivalent to the change in the current flowing through that wire. Okay, this EMF is proportional to di by dt. Here proportionality constant is again L in this case. Okay, what is the direction of this induced EMF? It is opposite to what? Rate of change of current. That means the creation of this, okay, it works as if it stops the change in the current. Okay, the change in the current itself is a cause of this EMF of self-induction. Okay, so this induced EMF is trying to oppose the change in the fluctuations in the current within the coil. Okay. Another important characteristic which I want to remind now is on what factors this L depends. You may think that L depends on I. No. L does not depend on I. It depends for a particular wire of particular shape. It is constant. It depends on the size and shape of the coil. or the loop, but not on the current flowing through that coil. So this inductance is some intrinsic property of that coil. Current is an external thing. We are bringing the current and allowing it to flow through that coil. It does not change the property of that coil. So inductance is an intrinsic property of any coil or a conducting loop. Okay, so it depends upon the coil. What is the meaning of that? Length and area or the dimension of that coil, length and shape of that coil. Okay, it depends on the dimensions of any particular coil. One coil, you always have one L for one coil, but it does not depends on L. Okay, inductance L of a coil does not change just by changing the current. Why? Okay, in the electrostatics you have some Q is equal to CV. C does not change. Capacity of a capacitor does not change just by putting more and more charge here. This is a ratio Q by V. This is a ratio between Q and V. Q and V. See, these two things. Q is a charge, V is a potential. And just like this, C is always constant. So for any one particular conductor, this capacity is constant. So for any one particular coil, your L is constant. Your L is constant. It is just phi by I. If you are increasing the current, then what is L? Your L is, here I am writing, phi by I. Your L is phi by I. As you change I, phi also changes. So this L is always constant. So L does not depend on I. Okay. Uh, this is what the important thing you have to remember. L does not depends on the current flowing through a wire. It depends on the shape and size of the conductor. You understand perfectly whenever we consider a particular concrete example. Okay. At the end of the class, we will consider the solenoid, and we derive the expression for the self-inductance of the solenoid. If you have that expression independent of current, then you come to the conclusion that the inductance of any conductor does not depends on the current. Okay, we will see that at the end of the class. So whenever we take one example, then this concept can be understood very easily and clearly. Okay, that we will do at the end of the class. Okay, right. So now where we have stopped, our induced EMF. Our induced, what is this? Self-induced EMF, ES, is equal to minus L di by dt. We have to note this direction. See, the direction of this ES is such that it abates, it stops the di by dt. So it takes care of keeping the current constant over that wire. Okay. So what is the result of this EMF of self-induction? It takes care of stopping the changes in the current within the coil. This is very similar to our previous case where we discussed about electromagnetic induction. There, induced EMF, what is the effect of the induced EMF? What is the result of induced EMF in the ordinary electromagnetic induction? It is induced in such a way that it stops the changes in the magnetic flux occurring there. So it takes care of keeping the magnetic flux constant. Okay, it tries to maintain the magnetic flux through the coil constant. Here, what is happening in the self-induction? Here, the self-induced EMF is seeing that there is no change in the current flowing through the wire. Why? Because it opposes the changes, fluctuations in the current flowing through that wire. Flowing through that wire. Okay. So we use inductors in our daily life. What happens in the inductors? It does not allow for the fluctuations of the current. Okay, we use these inductors as jokes. Okay, you know. Right. So what is doing induction here? Hmm? What is doing induction? Induction is some equivalent of inertia in mechanics. Inertia in mechanics. Inertia is defined by which quantity in mechanics? Inertia is expressed in terms of m. You have small m for one object, then mechanical inertia is small. You have large m for an object, then you have large inertia. In the same way, the inertia is expressed in electricity by means of the physical quantity known as inductance. In mechanics, which quantity give you the inertia, mechanical inertia? M. So there is a correspondence between L and M. L and M. See, the role played by M is played by L in the role played by M in mechanics is played by L in electricity. Okay, the same role is played by the L in electricity. Okay. What is the advantage of having the circuits more inductance? If you are having the circuits with more inductance, then what happens? Just switching on and off in that circuit will not drastically reduce the current flow or drastically increase the current flow. Suppose that you are connecting a battery to the circuit and you are disconnecting the battery to the circuit. If your circuit is having more inductance, okay, it is able to withstand these sudden things. That means whenever you connect to the battery, you have to notice abrupt current. But that does not happen. That is due to the inertia. Early in the earlier case, whenever you have no battery, there was no current in the conductor. That is a state of that conductor. The conductor tries to stay in the same without no current stage. That's why you do not have immediately surge of current in the circuit. Okay, the same thing happens when you disconnect the battery. Immediately, actually, you have to get no current in the circuit, zero current. But that does not happen. See, the induced EMF compensates for that current. It generates some current. That's why you find current for some time. Slowly, the current decreases in the circuit due to this self-induced EMF. This is supporting the change. This is compensating for that decrease or increase of the original EMF. Okay, that you have to note. This is what lagging effect. Whenever you disconnect the battery, current has to fall. But it is lagging behind in falling due to this self-induction. Again, okay, whenever you are connecting the battery, there should be a surge in the current, but that is not happening. It is not taking up the surge immediately. So lagging is taking place here due to the inertia, that means inductance of the current. That you have to know. Okay, let us stop with this. Thank you.